This is the fourth video on the grade 12 topic work, energy and power, and today in this fourth video we're going to be looking at the conservation of mechanical energy. So let's kick off by looking at the statement of that law, and that's on page 17 of your notes. So let's go and find that. There it is. Needs to be learnt. Law of conservation of energy states that the total energy in a system cannot be created nor destroyed, only transferred from one form to another. So that's what we've been focusing on, is this idea that when work is done, energy is transferred to another form. If we go back to our notes here, we've got the principle of conservation of mechanical energy. So this is the version that we'll be focusing on to solve problems, and later on we'll focus on the law of conservation of energy. So on page 17 of your notes, you will notice that there is a statement for that principle. Let's go there. Here we've got the principle of conservation of mechanical energy. Notice the change in words here. Firstly, it's called a principle. Secondly, it's the conservation of mechanical energy only. And if we look at the statement, it says, in the absence of air resistance, so if we ignore air resistance in all our problems, or any external forces. So here we're talking about forces that are applied forces. There might be frictional forces. Those would be considered to be external forces, and if they are absent, if there's none of those, then the total mechanical energy of an object should be constant at any 2 points. So let's just talk about those external forces. The external forces would be doing work on the object and either adding mechanical energy to the system or removing it. So if we ignore or we consider problems where the external forces are not around, then the total mechanical energy of the object should stay constant. So here in our notes we talk about external forces being friction, any applied forces, and obviously normal forces do zero work on an object because they act at right angles to the displacement. So they won't change the mechanical energy of the object. So let's go and look at figure 1.22 of our notes, and we'll see a skier coming down a slope, and we're considering two points in the motion. We've got this point here high up on the slope, and the mechanical energy of that skier would be the sum of his potential and kinetic energies. That would be 1 point of the motion. At any other point in the motion, we should have the same amount of mechanical energy in the system, because we're ignoring any friction. There's no friction on the slope. The slope is frictionless. So while he goes down the slope, there's no friction along that slope, so there's no external force there. The only force acting on him is the gravitational force, and we know that to be a conservative force. Gravitational forces change one form of mechanical energy into another, but they don't add or take away mechanical energy from a system. I'll say that again. Gravitational forces change one form of mechanical energy to another. So over here he has lots of potential energy and maybe some kinetic, and over here he would have more kinetic energy and less potential energy. So the gravitational force that's acting straight down all the way that he goes down the slope is changing one form of mechanical energy to another. So we can consider the mechanical energy at the top here to be the same as the mechanical energy at the bottom, because there are no external forces acting on the skier as he goes down the slope. The next, I think let's do checkpoint 7 on page 19 of the notes. So we've got, let's go there in our notes. Here it is. Let's just try and identify some information here. We've got a cyclist moving at 9 meters per second as he enters the slope here at the bottom. And it says in the problem that he freewheels up this frictionless inclined plane. So freewheels, the implication here is that he's not pedaling and there's no external force. He's not providing any external force to the bike, and we simply got the gravitational force acting on him as he goes up the slope. As he goes up the slope, the only force acting on him is the gravitational force, and we know that to be a conservative force. It doesn't add or reduce the mechanical energy in the system. And what else can we get from this? We've got the cyclist has a mass of the cyclist and bicycle is 72 kg, so that we've got the total mass. And what do we need to find? We need to find the maximum height h reached by the cyclist. So he's coming in here at the bottom, he's freewheeling all the way up. He's going to slow down, stop at his highest point. And here we'd have kinetic energy at the bottom of this slope being converted to gravitational potential energy at the top. So let's go and attempt that question. So I want you to pause the video and attempt the question, and then come back to check your answer. Okay, so we've tried the question. Let's just go through it again. He's coming at 9 meters per second at the bottom, and he freewheels to the top. There's no external forces acting on him, so we can use the principle of conservation of mechanical energy to solve this problem. Let's make a statement that the mechanical energy at the bottom here, let's call it A, is exactly equal to the mechanical energy at any other point up the ramp, and we're looking for point B. Point B would be his highest point where he stops. So if he stops there, then his speed must be 0. Alright, let's identify what mechanical energies we have at A. So mechanical energy of any object is the potential energy of that object at A plus the kinetic energy of that object at the same point A. And mechanical energy at B is obviously then the potential energy at B plus the kinetic energy at B. If we go to our formulas, we know that at point A he's got 0 potential energy because he's at ground level, but he's got lots of kinetic energy. That's the formula for kinetic energy. And then at point B he's got lots of potential energy, but he's stopped, so his kinetic energy is 0. If we put the numbers in, the mass is 72, the speed at the bottom of the slope is 9, don't forget to square that, and at the top it's all gravitational potential energy. The mass is 72, acceleration due to gravity is 9.8, and the height is what we're looking for. What is this vertical height that he reaches? And if we solve that problem, we're going to get 4.13 meters. So that's the vertical height he reaches. Right, so that's applying the principle of conservation of mechanical energy. What I'd like to do now is an extra question. I want you to find the speed of the cyclist at point C, a height of 2 meters above the ground. So if we go back to our diagram, we can be looking for the speed at a point C, which is exactly 2 meters above the ground. So if you can pause the video and find the speed of the cyclist as he passes point P. Right, since you've tried the question, let's solve it and you can check your answer. Right, so we're applying the principle of conservation of mechanical energy. Mechanical energy at A would be exactly equal to the mechanical energy at B, because there are no external forces acting on him. Sorry, at C. And we already know the mechanical energy at A, because we had calculated it earlier. It was all of the kinetic energy of the cyclist, which turned out to be 2,916 joules. That was all kinetic energy. But now at C, we need to be aware that he has some potential energy and kinetic energy. None of these two are zero at point C. He's moving past C and he's a height above the ground. So he certainly has both types of mechanical energy. So let's put that in there. Potential energy at C plus kinetic energy at C. Right, the potential energy at C would be his mass times 9.8 times the height of 2 meters above the ground, plus he has some kinetic energy, half of the mass, and we're looking for his speed at point C. And if we solve that carefully on the calculator, we'll get a speed of 6.47 meters per second. Right, let's go on to another exercise. This one's also in your notes. It's exercise 2.2 on page 21 of your notes, and it's question 4. So let's go there. Right, there it is. We've got Tarzan is running in at 12 meters per second when he attaches himself or grabs onto a rope and swings in an arc up to his high point, where he finally stops for an instant in time. And the question's asking us to calculate this maximum height. So he's running in at 12 meters per second, grabs onto the vine, and he swings to a maximum height h, and we need to find that. So pause the video and attempt that question. Right, now that you've had a go at that, let's solve it. Right, mechanical energy at A must be exactly equal to the mechanical energy at B, because there are no external forces acting on him. You might say that the tension in the vine is an external force, but that's always acting at right angles to his motion, so it's doing zero work on him. So we can only consider the gravitational force acting on him, and we know that to be a conservative force. So mechanical energy at A is equal to the mechanical energy at B, and we've got zero potential energy because he's right on the ground level, so potential energy would be zero here, but he's got lots of kinetic energy. So half mv squared. At B, he comes to a stop, so he's got zero kinetic energy, and all of his mechanical energy will be in the form of potential energy up here at B. And if you notice, we haven't put any values in, but you'll notice that we've got the mass m on either sides of the equation in both terms. So we could cancel that, and we could write down an expression for the height reached, which is going to be v squared over 2g. And you'll notice here that the maximum height reached by any mass traveling at 12 meters per second doesn't depend on the mass in question. So what does the height depend on? It depends on the speed that he was running at and what planet you're on. So the acceleration due to gravity. So on Earth that's 9.8. Let's put those values in. He's running in at 12 meters per second, and the acceleration due to gravity is 9.8, and that's going to give us an answer of 7.35 meters. So we've conserved mechanical energy, but we've also noticed that the mass is the same on each side of the equation, so we've been able to cancel that and shown that the height that this mass moves through doesn't depend on the mass of the object. So your job now is to complete exercise 2.2 on pages 19 to 27.